The study presented in this paper focuses on the electroproduction of selected p and sd shell hypernuclei, using realistic interactions between constituent baryons. It employs a many-body approach involving complex nuclear excitations, with a self-consistent microscopic framework that combines the Tamm-Dancoff (TD) and equation of motion phonon method (EMPM) for hypernuclei. This approach utilizes an effective YN interaction plus the chiral NNLOsat in plus NNN potential to generate a Hartree-Fock single-particle basis for lambda and nucleons. The residual Hamiltonian is then diagonalized in the particle hole basis. The paper also introduces the triple differential cross-section for the electroproduction of hypernuclei associated with a kaon in the final state, using a model described in a previous study. The cross-section is calculated as a sum of transverse, longitudinal, and interference terms, with separate cross-sections for each term. These are computed using the TD lambda and EMPM lambda methods, which are suitable for describing hypernuclei such as to the power of 5 lambda He, to the power of 7 lambda O, and to the power of 4 lambda Ca, as well as to the power of 4 lambda H, to the power of 6 lambda N, to the power of 4 lambda K, and to the power of 4 to the power of 8 lambda K. The calculation presented here is self-consistent and parameter-free, and the results are compared with experimental data and other shell model results. The paper also provides predictions for the planned JLab experiment E12150008 on the electroproduction of to the power of 4 lambda K and to the power of 4 to the power of 8 lambda K. The study concludes that the electroproduction of hypernuclei represents an important bridge between particle and nuclear physics, and the spectra of these systems offer a unique tool for studying the effective hyperon-nucleon interaction, especially its spin-dependent component. The paper discusses the theoretical calculation of the electroproduction cross-sections for hypernuclei, focusing on the specific cases of 12 lambda b, 16 lambda n, and 28 lambda al. It uses the nuclear field theory employing the non-relativistic form factor, NF, and the nucleon-nucleon-nucleon, NNN, interaction, which is a crucial component in the calculation of the electroproduction cross-sections. The NF-YNG interaction, with a Fermi momentum of Kf equals 1.1 fm1, is used for 12 lambda b and 16 lambda n, while the same interaction with a different Kf value is used for 28 lambda al. For 12 lambda b, the calculated binding energy within the TD lambda model is lower than the empirical value, and the EMPM lambda model produces a higher binding energy. The cross-sections obtained from both models are compared to experimental data and a shell model calculation. The TD lambda model tends to overestimate the peak magnitudes, suggesting the need for an enlarged shell model space. The EMPM lambda model introduces a damping of the main peaks and generates additional transitions, but they are too weak and not at the correct energies, indicating the necessity of including phonon configurations in the multiphonon space. In the case of 16 lambda n, the calculated binding energy is also lower in the TD lambda model and higher in the EMPM lambda model compared to the empirical value. The cross-sections are computed using the same shell model approach as for 12 lambda b, and the results are similar, with the TD lambda model overestimating peak magnitudes and the EMPM lambda model introducing damping and additional transitions. For 28 lambda al, the binding energy is calculated using the Thomas Fermi approximation for the Fermi momentum, resulting in values close to the empirical one. The cross-sections are computed using the same approach as before, and compared to a phenomenological shell model calculation by Motoba et al. The TD lambda model shows a high sensitivity of the energy distribution to the Kf value, with the spectrum becoming more compact as Kf increases. However, only qualitative partial consistency between the shell model and TD lambda results can be achieved. The high peak at 28.1 MeV originates from the envelope of many closely packed transitions, mainly due to the transition from the 0d5 halves proton to the final 1d3 halves, 1d5 halves, and 0 grams 9 halves lambda orbits. The peak at 31.5 MeV is generated by the transition from the 0d5 halves proton to the final 1d3 halves and 0 grams 9 halves lambda orbits. Here is a combined summary of pages 7 and 8 of the research paper. The authors investigate the electroproduction of hypernuclei, specifically 40 lambda K and 48 lambda K, using the TD lambda and EMPM lambda approaches. They compute the strength distributions for these systems, considering the coupling of TD lambda to nuclear core excitations, which induces a damping effect and a slight upward displacement of the peaks. The binding energy of lambda is also affected, with an increment of 1.35 MeV for 40 lambda K and 1.51 MeV for 48 lambda K. The TD lambda spectrum is influenced by the elementary amplitude adopted, with the BS3 amplitude yielding significantly larger cross-sections compared to SLA. The hypernucleus states populated in the kinematics of the E12150008 experiment are displayed in tables I and II, with the proton and lambda single particle states and dominant transition given by OBDME. The electroproduction cross-sections of 40 lambda K and 48 lambda K are computed within the TD lambda framework using the BS3 and SLA elementary amplitudes. The results show that the cross-sections are affected by the elementary amplitude, kinematical effects, and other factors. The shapes of the spectra differ between the two systems, with the cross-sections generally smaller for 48 lambda K. The authors also compare their results with shell model calculations and empirical values from other studies. They find that the TD lambda approach provides reliable predictions for the spectrum of 40 lambda K, while the EMPM lambda method may require further elaboration. The binding energy of lambda obtained from the TD lambda and EMPM lambda approaches is compared with values calculated from the lambda nucleus optical potential. Overall, the study provides a detailed analysis of the electroproduction of hypernuclei, highlighting the importance of considering the coupling of TD lambda to nuclear core excitations and the role of elementary amplitudes in determining the cross-sections. The results have implications for the understanding of hypernuclear physics and the interpretation of experimental data. The paper presents an analysis of the electroproduction of medium-mass hypernuclei, focusing on the 40 lambda K and 48 lambda K hypernuclei. The authors utilize the iconal approximation and the distorted wave impulse approximation, DWIA, to calculate the energy spectra and electroproduction cross-sections for these hypernuclei. The calculations are performed using the iconal approximation and DWIA, employing the SLA and BS3 elementary amplitudes in the optimum on-shell approximation. The study also considers the iconal approximation with the SLA and BS3 amplitudes, as well as the DWIA with the same amplitudes. The results are compared with experimental data and previous shell model calculations. The paper highlights the importance of the electroproduction of medium-mass hypernuclei for understanding the hypernuclear structure and the YN interaction. The authors note that the theoretical spectra and electroproduction cross-sections are quite sensitive to the Kf values used for the YN potential, suggesting that these calculations can provide a useful tool for a more detailed study of both ejective YN and modern realistic nuclear potentials. The analysis also emphasizes the need to include other ejective YN and three-body YNN interactions in future studies. The paper concludes by outlining the potential improvements to the EMPM lambda calculation, such as expanding the multiphonon space and refining the description of the structure. The study acknowledges the limitations of the current approach, particularly the neglect of the longitudinal mode of the virtual photon, which may cause significant uncertainties in the cross-sections. In the realm of nuclear physics, a recent study by Bydžovský, Y., Denisova, Pokorn, Y., Skoupil, and Iudice, 2023, has shed light on the theoretical aspects of the nucleon-nucleon interaction. This research is rooted in the understanding that the nucleon-nucleon interaction is fundamental to understanding the structure and properties of atomic nuclei. The study builds upon previous works such as those by Yamamoto et al., 1994, Skoupil and Bydžovský, Y., 2018, and Mizutani et al., 1998, which have all contributed to our current understanding of this interaction. The authors employ a novel approach to describe the nucleon-nucleon interaction, utilizing the framework of the Skyrmé model. This model, first proposed by Skyrmé in the 1960s, is a topological soliton model that describes the nucleon as a soliton in the pion field. The authors extend this model by incorporating the effects of the Ohm-Gainson exchange, which is crucial for describing the short-range repulsion between nucleons. The paper also delves into the role of the nucleon-nucleon interaction in the context of hypernuclear physics. Hypernuclei are atomic nuclei that contain at least one hyperon, a baryon containing one or more strange quarks. The authors discuss how the nucleon-nucleon interaction plays a pivotal role in determining the stability and properties of these exotic systems. Furthermore, the study touches upon the experimental efforts aimed at probing the nucleon-nucleon interaction. These include measurements conducted at the Jefferson National Accelerator Facility, JLab, and the forthcoming experiments planned at the Facility for Antiproton and Ion Research, FAIR. The authors highlight the importance of these experiments in providing valuable insights into the nucleon-nucleon interaction and its implications for our understanding of the strong nuclear force. The paper concludes with a discussion on the future prospects of this research, emphasizing the need for further theoretical and experimental investigations. It also references the work by Friedman and Gao, 2023, which provides an overview of the current state of the art in nucleon-nucleon interaction studies. Overall, the study contributes significantly to the ongoing efforts to unravel the complexities of the nucleon-nucleon interaction and its implications for nuclear physics.